Hey everyone, and welcome to This Explainer. I am absolutely thrilled you're here today because we are going to crack the code on something that honestly sounds like magic. We're looking at exactly how engineers and hydrogeologists manage to find invisible water buried hundreds of feet deep underground. It's an absolutely fascinating blend of pure physics and high-stakes engineering.
Okay, let's dive into this. We are going on a really cool journey today, moving from basic physics all the way up to some complex, real-world engineering case studies. Our roadmap covers 1. The blind drilling problem. 2. Electricity and resistivity basics. 3. Explaining the ERS survey. 4. Mapping the ground layers. And finally, 5. Real-world ERS applications.
Section 1. The blind drilling problem. The high cost of guessing.
So, I want you to imagine for a second that you need to find the absolute best location to drill a water well, and you're standing out in the middle of this massive flat alluvial valley. One option is to just drag a huge drilling rig out there and, well, start guessing. You drill exploration wells maybe every 20 meters. Now, you might actually hit the perfect spot, or you might just hit completely dry rock. This kind of trial and error method is an incredibly expensive gamble. It just wastes immense amounts of time and money. So that leads us to a pretty big question. Is there a cheaper way to find water than just blind drilling? The answer is a resounding yes, and it all comes down to an ingenious method called the electrical resistivity survey.
Section 2. Electricity and Resistivity Basics, From Pipes to Physics.
To actually understand how we can see underground without digging a single hole, we've got to start with a little physics, specifically Ohm's law, and this core concept called resistivity, which scientists represent with the Greek letter rho. To make this easy to visualize, think of electricity flowing through a wire, kind of like water flowing through a pipeline. The electrical current, that's the actual water discharging from the pipe. The voltage is the water pressure pushing it along. And the resistance, that's the friction inside the pipe that's slowing the water down. Resistivity is just a fundamental physical property of any material. It's the resistance per unit volume, and we measure it in units called ohm meters.
So the crucial point here is that different materials beneath the Earth's surface react to electricity in super predictable ways. It practically acts as a subterranean decoder ring. If we're measuring less than 10 ohm meters, we're almost certainly dealing with clay or very salty water. If we measure somewhere between 10 and 500 ohm meters, bingo, we've hit the sweet spot. That's the typical range for an aquifer holding fresh, usable water. But if that number suddenly spikes over 1,000 ohm meters, well, we've hit solid, dry bedrock. Section 3. Explaining the ERS survey. Injecting electricity into the Earth. All right, so now that we know what our target values are, how do geophysicists actually measure these ohm meters when the rocks are buried hundreds of feet in the dirt? This setup brilliantly illustrates the Schlumberger array, which is an industry standard. We've got two outer metal stakes driven into the earth labeled A and B. These are our current electrodes, and they're used to inject electrical current directly into the ground. Then, sitting right in the middle between them, we have two inner stakes labeled M and N. These are our potential electrodes, and their whole job is to measure the potential difference, or the voltage, of that electricity as it passes through the earth beneath them. Let's walk through the exact field procedure step by step. First, the field team uses a powerful battery to inject current via those outer A and B electrodes. Second, they read the potential difference in millivolts using the inner M and N electrodes. But here is where the magic really happens. Step 3. By physically expanding the distance between those outer A and B electrodes, the electrical current is essentially forced to travel in a wider, deeper arc underground. The farther apart you push the outer electrodes, the deeper your electrical signal reads into the earth. It's like expanding your underground vision.
Now you might hear about another setup called the Winner Array, but for groundwater exploration, the Schlumberger Array is generally vastly superior. Why is that? Well, first off, it's significantly faster, because the field crew usually only has to move the two outer electrodes, leaving the inner ones mostly stationary. Second, it's actually more accurate. Keeping those inner electrodes fixed helps you spot random near-surface errors in your data. And finally, despite some mathematical confusion you'll occasionally hear out in the field, side-by-side comparisons prove the Schlumberger Array actually has a slightly deeper effective depth of investigation than the Winner Array. It just works better.
Section 4. Mapping the ground layers, reading the curves. Okay, so we're going to layer on the complexity now. We have a raw electrical data from the field, but how do we translate those numbers into a three-dimensional map of the subsurface? When plotted out, the data creates this visual story, mapping apparent resistivity against the electrode spacing. Now, what's really interesting about this is how a curve might start high, but then create a distinct, downward dipping bowl shape in the middle. That downward dip indicates the current has hit an intermediate layer with much lower resistivity. In groundwater exploration, that bowl shape is exactly what you want to see. It usually represents our target aquifer layer, safely sandwiched between more resistive soils and bedrock.
But let's see how this visual story builds when we hit the very bottom of our water supply. When the tail end of the curve shoots upward in a sharp, straight line, we're seeing what's known as the 45-degree angle rule. Because the line physically cannot go any steeper than 45 degrees on these logarithmic graphs, it tells us the electrical current has hit infinitely high resistivity. Basically, it means we have struck solid, totally dry basement rock. Our aquifer has officially ended.
Section 5. Real-world ERS applications, saving millions in the field.
So, we've mastered the basics and we know how to read the curves. Let's look at how this complex data actually dictates real-world high-stakes drilling decisions. Our first case study takes us over to a survey conducted in Birnin Kebbi, Nigeria. By running the Schlumberger array, the researcher successfully mapped out 5 distinct subsurface layers. You can see the progression: topsoil at the surface, giving way to claystone and then limestone. But the real prize was found starting at a depth of 15 meters. They hit a zone of high conductivity, which indicated a weathered and fractured basement rock full of water. Thanks to this highly specific data, they knew exactly where to site their boreholes, recommending a precise drilling depth between 15 and 30 meters to tap that aquiferous zone perfectly. No guesswork required.
The mapped electrical resistivity curves from that site quickly revealed a massive problem. They found an upper aquifer sitting in the recent sand deposits, but the resistivity values showed it was highly saline. We're talking packed with 25,000 to 40,000 parts per million of total dissolved solids. It was totally useless. But by pushing the survey deeper, the electrical data revealed a second, lower aquifer based in the Gauge Limestone Formation. This deeper layer had drastically lower salinity, making it highly viable for a reverse osmosis plant.
Based entirely on those electrical readings, their final engineering solution was brilliantly precise. They recommended drilling a massive test borehole down to 1,000 to 1,200 feet just to reach that cleaner lower aquifer. But, and this is absolutely crucial, to prevent that nasty, highly saline water from the upper aquifer from pouring down and ruining the well, they mandated that the borehole be sealed with bentonite clay all the way up to a depth of 600 feet. The survey didn't just find the water, it dictated the exact engineering required to protect it.
From shooting electricity into the dirt to mapping out complex three-dimensional layers of life-saving water, electrical resistivity surveys are just an incredible testament to human ingenuity. It takes the blind guesswork completely out of hydrogeology. So, I'll leave you with this final provocative thought. Next time you go to take a drink of tap water, what invisible, electrically charged layers do you think are hiding right beneath your own feet? Keep exploring, keep learning, and thank you so much for joining me on this explainer today.